we're going to unlock the instruction manual for reality itself. We're talking about the fundamental rules that run everything in our universe. So what is physics exactly? Well, at its very heart, it's the most fundamental science there is. If you think of reality as this giant, incredibly complex building, then physics is the original blueprint. It tells us what the universe is made of, how all the different parts interact, and why the whole thing doesn't just fall apart. To do that, physics looks at a few key things. We're talking about matter, the actual stuff that makes up you, me, the Earth, the stars. It studies energy, which is basically the power to make things happen, to cause change. And it looks at motion and forces, the how and the why behind every single movement in the universe. These ideas are the foundation for almost every other science, from chemistry to engineering. Now, to read that blueprint of reality, we first have to learn its language, and the language of the universe is motion. Before we can even begin to understand the forces that cause all this change, we need a really clear way to talk about the change itself. Okay, let's start with two ideas that sound the same, but in physics are totally different. If you're in a car and the speedometer says 60 miles per hour, that's your speed. It's just a number telling you how fast you're going. But in physics, direction is everything. Velocity is your speed plus a direction. So 60 miles per hour heading north, now that's a velocity. And this difference is crucial because turning a corner is just as much of a change as slamming on the gas pedal. And any change in velocity, we call that acceleration. Now, we usually think of acceleration as just speeding up, right? But in physics, hitting the brakes is also acceleration. It's just negative acceleration. Even making a turn while keeping your speed exactly the same is a form of acceleration because your direction is changing, which means your velocity is changing. The main thing to remember is this: acceleration is any change in motion. All right, so we know how to describe motion, but why does stuff move in the first place? What makes an object start moving, or stop, or change direction? To answer that, we have to jump in a time machine back to the 17th century and meet one of the smartest people who ever lived, Sir Isaac Newton. He came up with 3 laws that became the absolute foundation for how we understand motion and forces.
Newton's first law is all about something called inertia, and the easiest way to think about it is cosmic laziness. The universe has a sort of default setting. Objects want to keep doing whatever they're already doing. They have this built-in resistance to any change in how they're moving, and we call that resistance inertia.
And this slide breaks it down perfectly. An object that's not moving, like a book on your desk, is going to stay not moving forever. And an object that is moving will keep moving at the exact same speed in the exact same direction forever, unless some outside force messes with it. You've felt this your whole life. When a car stops short, your body keeps lurching forward, right? That's inertia. The only reason things on Earth eventually stop is because of invisible forces like friction and air resistance that are always working against them. Newton's second law then puts some numbers to this idea. It basically says that the amount of force you need to change an object's motion depends on 2 things: how much you want to accelerate it and its mass, which is just how much stuff it's made of. And a quick but super important note: don't confuse mass with weight. Your mass is the same everywhere, on Earth, on the moon, wherever. Your weight is a force. It's the pull of gravity on your mass. This law just makes intuitive sense, doesn't it? A bicycle has a pretty small mass, so it only takes a little bit of force to get it going. But a car? It has a huge mass, so you need a way bigger force to get it to accelerate at the same rate. It's a really simple, elegant idea. More stuff needs a bigger push. That's F equals m times A. Newton's third law is maybe one of the coolest ideas in all of science. Forces always come in pairs. You can never have just one force acting alone. If you push on a wall, that wall is pushing back on you with the exact same amount of force. It's always a two-way street. That book on the table? Gravity is pulling it down. That's the action. But the table is pushing right back up with an equal force. That's the reaction. We call it the normal force. And there is no better or more awesome example of this law than a rocket launch. The rocket's engines blast a huge downward force on all that hot gas. That's the action. And in return, the gas pushes back with an equal and opposite upward force on the rocket. That's the reaction. And it's that perfectly balanced, incredibly powerful dance of forces that literally lifts us off this planet and into space. So, we've covered motion and forces, but for anything to actually happen, for any work to be done, the universe needs one more absolutely vital ingredient: energy. If forces are the workers that build and change everything, then energy is the currency that pays them to do the work. Nothing happens for free. Now, energy shows up in a lot of different ways, but when we're talking about motion, 2 types are key. First, there's potential energy. This is stored energy, or the energy of position. A stretched out rubber band is just packed with potential energy. A huge boulder sitting at the top of a hill is storing up gravitational potential energy. Then you have kinetic energy, which is the energy of motion. When you let go of that rubber band, its potential energy instantly converts into kinetic energy as it goes flying. This leads us to what is, no exaggeration, one of the most unbreakable laws in the entire universe, the law of conservation of energy. It says that energy can't be created out of thin air and it can't be destroyed. The total amount of energy in a closed system is always the same. It can only be transformed from one type to another. And the best place to see this in action is on a roller coaster. So, picture a roller coaster car. It's click-clack-clicking its way up that first giant hill. With every foot it climbs, it's building up more and more gravitational potential energy. Right at the very top for that one split second, it's almost completely still, just loaded with the maximum amount of stored energy, waiting to be let loose. And then it tips over the edge. As it races down that track, gravity takes over, and all of that stored potential energy rapidly starts transforming into kinetic energy. The car picks up speed, more and more speed. Its height is being converted directly into motion. And right at the very bottom of that hill, the car is going as fast as it possibly can. At that point, it has maximum kinetic energy and pretty much zero potential energy. The energy didn't vanish, it just changed its form, from potential to kinetic to power that incredible ride. Okay, so why does any of this matter? Motion, forces, energy, these aren't just abstract ideas you read about in a textbook. They are the silent, invisible engines that run our entire modern world. The real payoff for getting these rules is when you suddenly start seeing them at work absolutely everywhere you look. That device in your pocket, maybe the one you're watching this on right now, is a complete masterpiece of applied physics. The laws of electricity and magnetism are what power its battery. The bizarre rules of quantum physics are what make its computer chip work. And the physics of waves, light waves for the screen, radio waves for the signal, are what connect you to the rest of the world. And what about our biggest adventures? Every single satellite we launch into orbit, every probe we send to another planet, is a direct result of us understanding the laws of motion and gravity that Newton figured out centuries ago. We are literally navigating the solar system using 17th century physics. It's incredible. In the end, physics isn't just a bunch of formulas to memorize for a test. It's the language that our universe is written in. By understanding these fundamental rules, you're not just learning science, you're learning how to read the blueprint of reality itself. And honestly, what could possibly be more amazing than that?